Okay, so I'm thinking of maybe coming up to Valentine a week from today and bringing some new lab equipment and maybe doing a lab, one of the first labs or something with you guys. Is it next Friday a good day, you think? Yeah, okay.
Yeah, that'd be great. I think Jared won't be here. He'll be gone all next week.
Okay, well,
But other than that,
all right, well, we'll be okay with that. I will look into maybe getting a car to come up there and seeing what I can do, but tentatively that's what we'll do, and then we'll get you guys started on some labs.
okay.
And Lacey, you and I need to figure out a schedule for you to do labs at some
I
point.
agreed on Wednesday.
Wednesday, unfortunately, well, I could do Wednesday in the morning, like probably at 11 or something, maybe.
That works.
Okay. All right. So let's go ahead and get started today. Looks like we've got everybody on who's going to be here with us. I believe last time we finished up talking about, we were talking about capacitors still, I believe. And we finished up the chapter on capacitors and potential. And I think that we have some homework questions probably. That's my guess anyway. Because I did get some questions by email. When is the homework due?
Yeah, we probably need to move that. Jared, too, will be flying out to where he's going to be gone, and he won't be there till Monday, I think, till he gets, so yeah.
Okay.
Monday or Tuesday, at least, I think, for him. I don't know if we could all just maybe, probably Monday would be good in case this weekend we don't finish our questions.
Let's go ahead and put it till next Monday. And then we'll change things if necessary. Let's see, did I get my recording started? Can't tell. It is recording. Okay, good. All right. So yeah, let's go ahead and answer some questions about homework. I think that, yeah.
Well, I haven't been able to figure out number 3, so maybe we could just start there.
All right, let's do it. Number 3. Oh yeah, somebody else had a question about this too, so it's a good one. So a Van de Graaff generator is, I think we talked about that at some point, what a Van de Graaff generator is. I can't remember which part of the chapter it was in, or I want to say it was pretty early on, but I can't remember. Might have been in the last chapter too, but anyway, the Van de Graaff generator, in case we didn't talk about it, is a device that looks like this. Let me draw it. Where's my drawing? Here we go. It has a kind of a sphere at the top, and then it's got this stand that's made of like plastic or something non-conductive that goes down to the bottom, and then at the bottom here it's got a motor in it, And there's a belt that goes through the whole thing, a rubber belt on it's got a pulley down here like a wheel, and a wheel up here, a pulley up here, and this rubber belt that goes all the way down this thing to the bottom, right? And what it does is at the bottom there's a comb connected to ground that's made out of metal, and it's really close to the rubber belt, so sometimes it's even touching the rubber belt, but it really just needs to be very close to it, and that's connected to ground out here so that it can collect electrons. And then as the rubber passes by the belt, it picks up electrons from the comb, and it brings it all the way up here, and at the very top there's another comb that takes the electrons off the belt and puts them on this metal sphere up the top. So this is made of metal, and you can get a lot of electrons hanging out up here at the top. Can be really charged up, so you can get a lot of potential difference between the top and the bottom. You can get enough electric field built up so that it will actually strike lightning to things that are close by. The way that they design these is so that you can only, so that this sphere can only hold enough charge so that it won't strike lightning to wherever this is sitting, wherever the bottom is sitting. So the height of it and the size of the sphere is designed specifically to prevent it from striking lightning to the base, striking lightning down here to this comb, for example. So if you have a bigger sphere, you need a taller tower for it, in other words. And they're used these for all kinds of different things, but I mean, really, in the end, this is just a sphere that's a metal sphere that's all charged up. So one of the things that we've learned about metal and charges is that if you charge up metal, of course, the charges spread themselves out evenly all over the outside of the metal, because the charges are allowed to move very easily. They have free electrons in the metal. So what you're going to get is this very uniform distribution of the charge all around the sphere. And that means the further you get away from this, the more and more this thing just looks like a point charge with some charge on it, with some negative charge on it, right? So it's got, it's a point charge Q with some charge on it, the further and further you get away from it. And in fact, even if you're in close and you measure the electric field from here, the electric field just looks like a point charge that is centered in the center. It looks like there's a point charge centered in the center here, as long as you're outside of the metal sphere. So it behaves, the electric field, it behaves just like a point charge. If you're outside the sphere, it has these field lines that are coming in towards it like this. And they come in at like the spokes on a wheel if you're looking in 2 dimensions, but they come in from all directions, nice and spread out uniformly and everything. If you're inside the sphere, however, you get fields that cancel each other out, because you have this field going this way on this side and another on the exact opposite side of the sphere going the other way. And so the electric field, if you're anywhere inside of this sphere, is completely zero. So to calculate electric field around the sphere, all you have to do is use the equation for a point charge at whatever distance from the center of the sphere. Now, in this particular problem, they want to know what is the electric charge at, let me grab the assignment really quick. Where did it go? I don't know where it went. Somewhere. Hold on a second. My pointer is not working. There we go. Where did it go? I don't know. Oh, there we go. So in this one, they say they want, they've got this sphere that has a radius of 0.5 meters. So we know the size of that sphere, and it has this charge on it, and they want to know what the force is or the acceleration of the electrons when they leave the surface. So we've got this sphere now. Go back to my drawing here, and we're on the edge of the sphere, and it's like we're a little electron here on the edge of the sphere with this negative charge, negative E, the charge of an electron. And we're going to go accelerating away from here. And of course, if we're feeling an acceleration, then there's a force that we're feeling that's equal to the mass of the electron times the acceleration. Right? So what we have to figure out, we have to look up the mass of the electron, first of all, and we need to figure out what the force is. Then we can calculate the acceleration, because the acceleration is just equal to the force from the electric field over the mass of the electron. So the mass of the electron is like 9.1 times 10 to the minus 31 or something like that. I don't know exactly what it is, but it's some super tiny number. And you can look that up. It's in the back of the book in one of the appendices or something like that, or you can just look it up online. Look at the mass of an electron, very tiny. You'll need that eventually. But what we really need to do is calculate this force. And one of the things that we do know is that the force from an electric field on a charge is equal to the charge times the field, Q times E. In our case, we know that the Q is going to be the charge of an electron, which we call negative E, which is 1.6 times 10 to the minus 19. But we don't know what E is. We don't necessarily need the negative on there. That's not necessary because we're just looking for the magnitude. But we need to know what E is. And so we have to calculate the electric field. The electric field is equal to the charge that creates the electric field, which would be the charge on the sphere, divided by the distance away from that charge that we're trying to calculate it. And remember, we said that the electric field at the edge of the sphere is going to be as if we were calculating the electric field at a charge that's at the center of the sphere. So we're going to use our distance r to be the radius of the sphere. So we divide by the radius of the sphere squared, because we're doing it at the edge of the sphere. And then we multiply by the Coulomb constant K. So this is the electric field, K times Q over R squared. We have all those numbers. Here's our Q. Our K is, the 8.99 times 10 to the 9 or whatever it is. I think that's what it is. And then the Q, then the R is the 0.5 meters. You're going to get your value for your electric field here, and then you're going to plug it into here to get the force, where E is 1.6 times 10 to the minus 19, the charge of the electron. It is so hard to do this on I always forget my mouse. I have to go find my mouse, see where it is. But anyway, plug in. So this charge here, the charge of the electron, is different than this charge here. And that's something that I think people might confuse. When you're calculating the electric field, you use the negative 95 microcoulombs. You don't have to use the negative. The negative's not important. We're just looking at magnitudes. But then when you calculate the force on the electron, you take this electric field, put it here, and use the charge of the electron then instead. Different charge there. And that will give you the force that the electron is feeling. And then you plug that force in over here and divide it by the mass of the electron. And you should be able to get the acceleration of the electron at that point. And that's how that's done.
Yeah, I wasn't even thinking about the electron, the force on the electron.
Yeah, and that's actually the thing that we're doing here in this second half
Well,
of
not
this
the
class.
force, the charge.
Oh yeah, the thing that we're doing in the second half of this class is we're taking all the stuff that we learned last semester, and we're kind of sticking it in our back pocket because we're going to use it every once in a while. But then when we when we're dealing with charges, we have to think differently in terms of what's the force on a charge, but that's also still equal to mass times acceleration, according to Newton, right? So, so it's a little bit confusing at first as we kind of get used to combining the knowledge from last semester with the knowledge this semester. But it's definitely something that we'll do a fair amount of. So,
Can you check how close my answer was
how close your answer was on this problem?
for, yeah, that particular problem?
Hold on a second. What kind of answer did you get?
I got 4.5 times 10 to the 30th.
10 to the 8th?
No, to the 30th.
To the 30th. That sounds much too big.
Mhm.
That's an acceleration that is crazy, crazy big. But I can check just really quick. My guess is that you did something wrong in the calculations with the exponents, because there's a lot of exponents in there. Remember, there's the K constant, which is 9 times 10 to the 9. There's also the nanocoulombs, the charge, which is 10 to the minus 9. So you have to put in the nanocoulombs. Many students forget to do that. So that your charge should be whatever your charge is times 10 to the minus 9. So essentially the K, the exponent in the K and the exponent in the charge are essentially going to cancel each other out. You're going to get 10 to the 9 and 10 to the minus 9. And that, of course, just equals 1 when you multiply them together. And then you have the 10 to the minus 31 that you're dividing by. And you also have the something else. You're the charge of the electron, which is a 10 to the minus 19. So there's a lot of back and forth with big numbers, small numbers, multiplying and dividing. But let me take a look here really quick at that question for you, if I can. It's certainly not. It's certainly much too big of a number here. Which chapter is this? 19? Yeah. Okay. Goodness, my computer is being slow, or the internet's slow. So you did 4.5 to the 30. So your number 4.5 is fairly close. It's off by a little bit, and that just might be the numbers that you plugged in and some rounding error, but it's fairly close. But the 10 to the 30 is definitely off quite a bit. You should be somewhere closer to like 10 to the, I think the answer that I got was a 10 to the 16 or a 10 to the 15 or maybe even a 10 to the 14, somewhere in that range for your acceleration. So a much smaller, still a big number, but a much smaller than 10 to the 30. It shouldn't be more than, I would guess it shouldn't be any more than 10 to the 17 and shouldn't be any less than probably 10 to the 15. It should be somewhere in that range between 15 and 17, depending on your numbers. So, okay. So, who else has a question of a problem that they'd like to take a look at?
Can we check out 10?
Check out number 10. Yes, we can. I'm accidentally showing everybody's grades. That's not good. Sorry. Okay. So number 10 is, where's my homework? Here it is. Okay. Number 10. Rectangular parallel plates. They have an area A separated by distance D. Then we connect them to a power supply, charge them with a voltage. There's no material between them, and they get a capacitance of C. The electric field is E, and the energy stored is U. Okay. So this one is a bit tricky because I'm not giving you any numbers here. So you have to do it all with just symbols, right? So it's everything it has all the normal stuff about a capacitor, and they want to know what is the capacitance. And then the last thing that they say is, well, it's still connected to the power supply. The plates are moved, so the distance between them is double what it was. So D becomes 2 times D, essentially here, right? So it would be a good idea for us to remember to go to the section on capacitors here, which is right already open here, and look at some of the equations. So C equals Q over V, or Q equals CV is one of them. Another one that's going to be quite relevant for us is this one right here. C equals epsilon naught A over D. That's a good one to remember. And then also the one about the maybe the electric field. The electric field equals voltage over distance. That's maybe a good one for us to remember. And the last one that I would say is going to be important is the energy, which I think is on in the next section. So the energy of a capacitor. No, that's not it. Next section still. The energy stored in a capacitor, which is you can do a QV over 2 or CV squared over 2 or Q squared over 2C. So lots of different equations that we can possibly use. So the capacitance, first of all, if D changes to 2D, how does the capacitance change? Well, we need to know what the capacitance is to begin with. The capacitance to begin with looks like this. C equals epsilon naught A over D, right? That was one of the equations that we had. And if D changes to 2D, then we're going to get a 2 down here. Instead of just D, we'll have 2D down here. And that means our capacitance has been changed by 1/2. So that means our capacitance will change by 0.5. Okay. Now we also know that Q, like C equals, let's see, what is it? It's C equals QV, I think. Q equals CV. I can't remember which one the other one is. I think it's Q equals CV. I think that's it, and then you can solve that. So another equation says Q equals CV, and that means that C equals Q, or V equals Q over C. All right. And they want to know how the voltage is going to change. Well, if the capacitance changes by 1/2, and this equation is true, then voltage will change by 1 over 1/2, which is 2, right? And so on and so forth. There's an equation for the electric field. And they have an equation for the electric field as a function of the capacitance. And we know how the capacitance changes. The capacitance goes from this to epsilon naught A over D, A over 2D, rather. So it changes by 1/2. If the capacitance changes by 1/2, the voltage changes by 2. Well, how does that affect the equation for the electric field between the two? How is it going to affect the Q, which we can use this equation for again? How does it affect the energy that's stored on the plates, which we would go and use one of the energy equations, whichever one you want to, depending on how you want to do it. So that's kind of how you go through and do all of these. Does that make sense?
Yeah, it does.
So you just go one by one and pick the equation that's going to help you to figure out that relationship, how it changes. All right. So we've done number 3, we've done number 10. What else do we got? Any other
Same thing with
questions?
number 11, right?
Number 11, okay. So the capacitor is constructed of 2 metal rectangular plates, dimensions 20 by 26. So from those, we'll be able to calculate the area, right? 20 centimeters by 26 centimeters. Don't fall into the trick, or don't fall into the trap that says the area is equal to 23 times 26. What should it be? This is not true. What should it be? Anyone? I'll give you a clue. What should this calculation look like instead of 23 by 26?
Should be 0.2 and 0.26.
Yeah,
Change it into
0.23.
meters.
Change it into meters. That's correct. That'll give you a very different answer. 0.26, right? Okay, so that's our area. A plastic film between them that's 1 millimeter thick. What does this tell us about the capacitor if the plastic between them is 1 millimeter thick? What does that tell us?
Distance in between them.
Distance.
So it's gonna hold a lot of charge.
So it's distance equals 0.001, 1 millimeter, right? So that we know the area, we know the distance, and that means we can calculate the capacitance of this, unless there's a material in it. Of course, there is a material in it because the plastic is the thing that's the 1 millimeter thick. So then now we need to know the dielectric constant, which they do tell us, dielectric constant of 2.3, and a dielectric strength of 60 times 10 to the 6 volts per meter. Now there's different ways to use these two numbers, and we have to remember which one is which. There's different equations to use these two numbers in. So if we go back to the book and look up the section on capacitors again really quick, which is right here. Go down to the bottom of this section. Dielectric. So here they use this form of the equation for calculating the capacitance that uses the area and the distance, which is what we have, and then it uses this kappa, and right here that's called the dielectric constant. That's not the dielectric strength, and they did give us the dielectric constant. So this is the equation we want to use. It wants to be kappa epsilon naught A over D. So since that's what we've got those numbers, we might as well use them. So we go back here, we've got our capacitance is now equal to our kappa, which is the dielectric constant. That's this one right here. This equals kappa. Funny looking K. So we put in our kappa, and then we multiply by epsilon naught. You got to look that up. And then you multiply by A that we calculated, divide by the D, 0.01001, and that will give us our capacitance. So that's useful. Now, they tell us that it's charged with a 6-volt battery. So they tell us the voltage. Well, that's useful too. They give us the voltage, that's equal to 6 volts. So now we know the capacitance of our capacitor, the voltage of our capacitor, and then they tell us that they're using this capacitor to lift a 50-gram weight. In the unrealistic assumption that it's 100% efficient, how high will the weight go? Well, if it's 100% efficient, that means that all of the energy that is inside the capacitor will be used to lift this 50-gram weight. Well, energy to lift a weight is always m times g times h. It's the potential energy. So that's the amount of energy, where the height is the height that the weight will go, g is 9.8, and m is the mass of the weight. So that's how much energy is going to be used to lift this weight. But the energy that's available in the capacitor is equal to something, the capacitance times the voltage, or in some way. There's something combining the capacitance and voltage that's going to give us that, because those are the two things that we have. And if we go back to our book again, looking at our book, I got to switch to that. Okay. Go back to our book and we look at the energy in a capacitor section. If this can do this, there we go. When you have the capacitance and the voltage of a capacitor, you can use one of these equations to calculate the energy, and this one has the voltage and the capacitance. We have, it's CV squared over 2. So we can use that to calculate the energy. We go back here and we put that right here. MGH equals CV squared over 2. Then all we need to do is solve this equation for H. It's going to get H equals CV squared over 2mg. And then you plug in all the numbers that we've got. And that will tell you the height that it can be lifted to. It's not actually true, because it's never 100% efficient to go from electricity to lifting things. But if we wanted to go to a higher height, what things could we change to make that happen? So when we solve this equation, height equals CV squared over 2 times mg, if you increase the capacitance, you'll increase the height. So right here, what things here will increase the capacitance? We come over here to our capacitance equation. If K increases, then the capacitance increases. So that's the dielectric constant. If that gets bigger, dielectric constant gets bigger, then this can go higher. If the area of the plates gets bigger, of course, then you can do that. And there's a bunch of things that can change. And you can even talk about the voltage. So you can look at the capacitance or you can look at how, if the voltage changes, does that change the amount of energy available? And that's how you'll decide which of those things will actually increase the ability of this thing to go higher. And I told you 2 of them, but there's more than 2 of those that will actually help to increase the height that you can lift it to. I'll let you figure out the rest. Does that make sense for you? All that stuff?
Yeah.
Okay. Good.
So what about the H max there?
The bottom here. Hold on a second. I can't read it all the way. Capacitor originally described can be charged on maximum voltage. So if the capacitor, as originally described, could be charged with the maximum voltage before dielectric breakdown occurred, how high would the weight go? Okay. So in this case, we'd have to figure out what is the maximum voltage we can charge this to. So they've told us they charged it to 6 volts, but there is a maximum depending on the dielectric strength. And so we got to go back to the book and remember what we learned about dielectric strength. We go back here to capacitors and dielectrics. We go down here to the part on dielectrics, the dielectric constant and dielectric strength. Here they talk about the dielectric constant, and here they list the dielectric strengths. Here they also talk about the dielectric strengths. Here is where, let's see, no. Yeah, here we go. So the maximum electric field strength above which an insulating material begins to break down and conduct is called its dielectric strength. So the list of dielectric strengths that we have tells us how high the electric field can be before this thing gives out, right? So in our particular case, we had plastic, which they don't necessarily list here, but they told us what the dielectric strength is. And then we don't want to use the equation for the electric field, which is actually right here. So this equation right here, the voltage equals the electric field times the distance. If you put in the dielectric strength into this part for E and multiply by the 1 millimeter distance, that'll tell you the highest voltage that you can get. So in this equation, dielectric strength goes in for E rather, because it is an electric field measured in volts per meter. So our dielectric strength in this problem looks like it is dielectric 60 times 10 to the 6. So 60 times 10 to the 6 times the 0.001 would give us the voltage that we can hit. And then that voltage would be used in this equation right here to calculate the height again, the maximum height.
Okay, that makes sense.
Excuse me, man. I fell asleep right before we got we started this class, and so I'm a little groggy. I came home early today, and I'm teaching from home. Okay, any other questions? We've got time for maybe one more quick one. No more?
I had a question on number 9 for just calculating the last part of the question.
So the potential energy. So again, this is the one that has the several different ways of calculating the energy for a capacitor. And the reason that there are several different ways is because you come out with this, you get this equation here. It's charge times voltage, but the charge and the voltage are related to each other in a capacitor because Q equals C times V. They're related by the capacitance. So you can get these three different ways to calculate the amount of energy stored in a capacitor. And whichever one has the two things that you know, is the one you should use. So if you know the charge and the voltage, then you should use this one. If you know the capacitance and voltage, you should use this one. If you know the charge and the capacitance, you should use this one. In this particular problem, they have told you, question 9. So they've told you the capacitance is 100 picofarads, and they're told you, they've told you the voltage. So you know C and you know V, right? So you could do, and actually you actually calculate Q in the previous part here. So you can use any of those equations to calculate the potential energy. To calculate Q here, you're just going to multiply C times V. And then to calculate U, you can do any of the three equations in the last section that you want. It's up to you entirely. Does that make sense?
A little?
A little bit. So right here, they've told you, you've used this part. Did you do the first two parts of the question already?
I did. I don't know how Q factors in to figure out that very last part.
Well, the last part is there are the formulas, and so you're just using the formula. These are the formulas right here. It's the energy equals QV over 2, and you have both of those. You have both charge and voltage. The charge you just calculated, the voltage they give you. You can use CV squared. You can use the voltage squared times the capacitance, which they give you the capacitance and they give you the voltage. So you could just use both numbers that they give you. Or you could use the charge that you calculated divided by the capacitance they give you and also 2. So you do charge squared divided by 2C. any one of these will give you the same exact answer for the energy stored by that capacitor because of the relationship Q equals CV. So it's kind of, for that particular problem, it's any one. You can use any one you want. So, and that takes us just about to the end of the class. I believe we're right on the bell should be ringing soon, right?
Yeah, we're actually supposed to be gone. So,
All right. Well, have a good weekend, and we will see you on Monday.
all right, great.
ya.
Thanks. You too.
Yeah.